Good morning. Thanks for joining us. I'm Doug Cobos, Director of Research and Development here at Decagon Devices, and today I'd like to talk to you about something that's pretty near and dear to my heart, and that's the accuracy of dielectric soil moisture sensors. And in particular, I want to answer a couple of questions, and one of those is a question that we used to get a lot here. It says, why does my soil moisture sensor read negative? So here's a brief introduction to the things that I want to talk about today. First, want to define volumetric water content so we're all on the same page, and then talk a little bit about direct versus indirect measurements, and then specifically about direct versus indirect measurements of volumetric water content, and then finally zero in on one of the indirect techniques for measuring volumetric water content, which is through the use of dielectric permittivity. Then I want to change gears a little bit and start talking about accuracy. First of all, defining accuracy, and then also showing you the approach that I want to use to do an accuracy analysis of the volumetric water content measurement with the dielectric permittivity probes. Then I want to talk about three different main factors that affect that accuracy, which are sensor accuracy, then also the relationship between dielectric permittivity and volumetric water content and how we can improve that relationship, and then talk about proper sensor installation and how that can help the accuracy of your volumetric water content measurement. So first of all, let's define volumetric water content. Volumetric water content, or volumetric soil moisture, is simply the volume of water contained in a total volume of soil. So in this little picture you see here, we have 1 cubic meter of soil. In a typical mineral soil, maybe half of that, or 0.5 cubic meters, is your soil mineral component. In this case, it's a pretty moist soil, so about 0.35 cubic meters is water, and then the remainder, about 0.15 cubic meters, is air. So in this case, the volumetric water content, or volumetric soil moisture, would be the 0.35 cubic meters of water divided by the 1 cubic meter of total soil volume, which gives you 0.35 meters cubed water per meter cubed soil, or 35% volumetric water content. Now, because that's a unitless quantity, because you're dividing meters cubed by meters cubed, you can use percent to talk about that, but don't mix that up with 35% water content on a mass basis. So there's also gravimetric water content, which is measured on a mass basis, which is not the same as volumetric water content. For all field measurements of water content, all of your sensors that you would use to measure water content in the field, those all measure volumetric water content, and so that's what we'll be talking about today. Now we want to talk a little bit about direct measurement techniques versus indirect measurement techniques. A direct measurement technique, as the name indicates, is when you simply directly measure the quantity that you care about. So for instance, you could measure length directly with a ruler or a pair of calipers. You could measure mass directly with a balance. But often we can't directly measure something, or can't conveniently directly measure something. So we would measure some quantity and relate that to the quantity that we actually care about. So with the indirect technique, an example of this would be a mercury or alcohol thermometer, where we are actually just measuring the expansion of the alcohol or mercury in the thermometer and using some calibrated markings on that thermometer to relate that expansion to the temperature of the mercury or alcohol. And so often we need to make that indirect measurement, and those can be done well, but they have to be calibrated back to the direct measurement. There is only one way to directly measure the volumetric water content in soil. So to directly measure water content, you need to obtain a known volume of soil. Okay, if you know the volume that you're working with, then that's the denominator, that's the volume of the sample. Then you would measure the mass of that soil while it's wet, dry it out in an oven, and then measure the mass of the soil when it's dry. The difference between the moist mass and the dry mass is the water that was lost during drying. Because the density of water is 1, the mass that was lost is the same as the volume that was lost, and so that gives you the numerator. So the volumetric water content, or theta there, is directly determined basically by loss on drying. That's the only direct measurement, and that's the measurement that all of the other volumetric water content indirect measurements are calibrated to. So keep that in mind. Today we will be focusing in on one of the indirect volumetric water content techniques, and that's the measurement of the dielectric permittivity of the soil, which we then can relate to the volumetric water content of the soil. The basis of this is that the dielectric permittivity of any mixture, and in this case it's our soil mixture, is related to the dielectric permittivity and the volume fractions of all the things that make up that mixture. So in soil, we have a mixture of a few things. We have some soil mineral component, okay, which you can see up there has a dielectric permittivity of maybe 3 to 16. We have air in the soil, which has a dielectric permittivity of 1, maybe some organic matter, 2 to 5. If we're working in frozen soils, then we have an ice component. But then you'll see that any water in the soil has a relatively high dielectric permittivity, 80 basically. So if you think about what happens during wetting and drying events in the soil, what really happens when you get precipitation or irrigation is that water enters the soil and displaces air. So you have a bunch of material that's coming in that has a really high dielectric permittivity of 80, and that's displacing a bunch of material, air, that only has a dielectric permittivity of 1. So this causes the bulk permittivity of that mixture to shoot way up. And the inverse is true in drying processes. When you have evaporation, well then the water's leaving and the air is taking its place, and this causes the dielectric permittivity of that mixture to decrease substantially. And this is how we can measure dielectric permittivity and then relate that to the volumetric water content. And we'll talk about this in a lot more detail in just a minute. This is an example of what that relationship looks like. On the x-axis, you see dielectric permittivity. On the on the y-axis, you see the volumetric water content. And so this is the famous Top equation that was first presented back in 1980 by Clark Top. And it is just an empirical relationship that relates dielectric permittivity to volumetric water content and allows you to predict water content from dielectric permittivity. And it's actually a pretty good relationship that works for a lot of typical mineral soils. And so this is the basis of our ability to be able to measure permittivity in the soil and get water content. This is one example of that anyway. So now let's switch gears just a little bit and talk about accuracy. What are we talking about when we're talking about accuracy? Well, today I don't want to talk about resolution. Okay, I don't want to talk about precision. I want to focus in a little bit on accuracy, which accuracy is how close we can get to the actual value. It's not what kind of change we can detect, that's resolution. It's not the degree of reproducibility, that's the precision. What I'm wanting to focus in on a little bit is getting our volumetric water content measurements as accurate as possible. Now, you may stop me and say, hey, wait a minute, I don't necessarily need accurate water content measurements. What I need are really precise measurements so I can see change very well. And that's true. In a lot of cases, you don't have to have a great degree of accuracy. Sometimes the precision is more important. But there are also a lot of cases that your research needs really accurate water content measurements, and that's what we're going to focus in on today is increasing the accuracy of those water content measurements. Now, what are we talking about the accuracy of? I just told you that we're not actually measuring water content in the soil with our dielectric measurements, with TDR, with frequency domain, with TDT. We're actually measuring the dielectric permittivity. So are we going to talk today about the accuracy of the dielectric permittivity measurement, or do we care more about the accuracy of the water content measurement? And the answer is obviously we care about the accuracy of the water content measurement. the accuracy of the dielectric permittivity measurement does play into that, and we will cover that, but that's a relatively small portion of what makes up the total accuracy of the water content measurement. So as we go along, the big picture thing that we're talking about is getting the most accurate measurements we can, but there are a couple of questions that I'd like to answer along the way. And one of those is a question that I used to get quite a bit back when I did a lot of customer support, and that is, why is my soil moisture sensor giving me a negative reading? So we will address that at a few points in the presentation. And I also want to address the question of, can a sensor really give you 1 to 2% volumetric water content accuracy for all soils? And the reason that this comes up is that often when different sensor manufacturers are writing marketing material or putting things on their website, there's a little bit of a sense of one-upsmanship when it comes to writing accuracy specs. And you will see on some manufacturer websites that they claim that their dielectric soil moisture sensor can measure water content within 1% or within 2% in all soils. And so we want to look at some of the factors that affect that accuracy and see if that is actually possible. So what's the approach that we're going to use today? Well, what I'm planning on doing is using a generalized dielectric mixing model. And what I'm going to do is set the parameters up in that model to reflect a quote-unquote normal mineral soil. And then we're going to vary those model parameters, all the inputs into that model, over the range that you might see in soils and see what that does to our predicted volumetric water content values. And I think as we go through the next couple of slides that this will make a little bit more sense. So let's take a look at the generalized dielectric mixing model. And it's got a lot of components to it, but it's actually extremely simple. So what you see here, if I can get my pointer to go, is that this is the bulk dielectric permittivity. This is related to the volume fraction of air multiplied by the dielectric permittivity of air, okay, and then you have these little alpha coefficients, plus the volume fraction of minerals, and this is the dielectric permittivity of the minerals. Here's the volume fraction of water, which is our volumetric water content, which is what we're ultimately trying to get at, and then that is multiplied by the dielectric permittivity of the water. So if you rearrange that equation and solve for the component that we actually care about, the volumetric water content, then you can do a sensitivity analysis. You can vary the bulk permittivity. This is what the sensor measures, so we're going to vary bulk permittivity over the range of sensor measured dielectric permittivity and see what effects that has. We're going to look at the permittivity of the mineral fraction and see what that does to our measured water content. We've broken this term out into bulk density and particle density. This is actually the volume fraction of minerals, and we're going to look at the effect of soil bulk density on measured water content, and we're also going to look at the effect of the dielectric permittivity of water on the measured volumetric water content. So that's how we're going to approach our sensitivity analysis, and we're going to look at each of those components and see how sensitive our measured volumetric water content is to each of those individual components. First thing I had to do though was parameterize this model and make sure that this dielectric mixing model is doing a good job of predicting what might be a typical soil. So what I tried to do, I just took the top equation, because the top equation, even though it's now 32 years old, is still a valid method and pretty reliable method for getting from dielectric permittivity to water content. So I selected some mixing model parameters that would allow that mixing model to line up more or less with the top equation. And you'll see down here on this side that we selected, of course, 1 as the dielectric permittivity of air. Mineral permittivity we selected as 4, which is generally a pretty good book value for the permittivity of most soil minerals. We selected 78.5 as the permittivity of water, which is, I think, the permittivity at 25 degrees. Selected a bulk density of 1.4 that is a pretty good general bulk density, and then a mineral density of 2.65 grams per cubic centimeter, which is also a good book value. And if you use those just normal soil values, you'll see from the graph that the mixing model does a pretty good job of approximating top, and we know that top does a pretty good job of approximating what we see in nature, so we feel like our mixing model is well parameterized at this point. So let's talk about the three factors that affect the accuracy of the volumetric water content measurement. The first is the sensor's ability to measure the dielectric permittivity accurately, and I'm going to call this the sensor accuracy. Okay, this is what the sensor is actually measuring, and so if the sensor is doing a perfect job, then we wouldn't have to worry about this, but no sensor at this point does a perfect job of measuring dielectric permittivity. Once we have our permittivity measurement, we have to take the next step and get that from permittivity to volumetric water content. And so the quality of that conversion or that calibration from dielectric permittivity to water content also introduces error. And so we will talk about the loss of accuracy that is attributable to that relationship that we use to get from permittivity to water content. And finally, we will talk about the loss of accuracy that you can get from poor quality installation of the sensor into the soil. So those are the three factors that we're going to talk about today. Okay, so now let's get into it. Let's start talking about our sensor accuracy. As I said just a second ago, the sensor accuracy is the accuracy with which the dielectric permittivity sensor can measure dielectric permittivity. Okay, this is the only specification that the sensor manufacturer can give. These sensors don't, of course, directly measure soil water content. They measure the dielectric permittivity. And this is all that myself or any of the other sensor manufacturers and sensor developers can control. So what are some of the factors that we have to control for, that we have to take into account to make sure that we give you a sensor that measures dielectric permittivity as accurately as possible? Well, we may not have understood this so well back in the early days, you know, maybe back in 2002 when we started making soil moisture sensors, but we certainly understand it now that one of the key things that we have to do is make sensors as repeatable as possible. That way, if you can calibrate them to dielectric permittivity, you can calibrate one sensor and that applies to all sensors. And so we have to control our processes so that each and every sensor reads the same. Now, a lot of sensors from us and also from other manufacturers are individually calibrated in standards of known dielectric permittivity, and this really helps increase the accuracy, but it also drives up the cost. So you'll see up there that most of our sensors at this point are calibrated sensors that we know pretty darn well how accurately those measure dielectric permittivity. So if we take that step, then we're pretty certain that we're giving you a good, accurate sensor. However, there are other factors in the soil that affect that accuracy. It is well known that the electrical conductivity of the soil can affect soil moisture sensors. If the sensor does a good job of either separating the dielectric permittivity from electrical conductivity or simply ignoring the electrical conductivity, then we don't have to worry about it. Back in the old days of the frequency domain sensors, for instance, when we first started producing the old EC10s and EC20s, those measured at a relatively low measurement frequency, and they had a pretty high sensitivity to salts and to electrical conductivity in the soil. Those were several generations of sensors ago, so we've certainly improved the measurement technology, as have other manufacturers, and almost all the sensors that you find now are measuring at higher frequencies, maybe 70 to 100 megahertz, which really minimize the effects of electrical conductivity unless you're in super high electrical conductivity and super high saline soils. And so in most typical soils, you don't have to worry about the electrical conductivity effects anymore. There also are effects of temperature on sensors. As Galen Campbell, the founder of our company, once said, you can use just about any sensor that measures anything and that'll make a good temperature sensor. So temperature affects pretty much all physical measurements, and so we have to take a lot of precautions to make sure that the temperature doesn't affect the dielectric permittivity reading. We've done that with our sensors. If you throw our sensors in a temperature chamber and cycle temperature, you'll see that there is virtually no inherent temperature sensitivity in the electronics of the sensor. However, when you put the sensors in the soil, there are things in the soil, electrical properties of the soil, that change with temperature. The dielectric permittivity of water itself is temperature sensitive. So as the temperature goes up, the dielectric permittivity goes down. Dielectric permittivity of water goes down. So if you're in a low electrical conductivity soil and you have diurnal temperature changes, then your soil moisture sensor will probably read a little bit higher at night than it does during the day, because the temperature of the water has gone down, and so therefore its dielectric permittivity has gone up. So you might see a little inverse correlation with temperature. I just said a second ago that most of the new soil moisture sensors have very low sensitivity to electrical conductivity in the soil, but I think probably all, even TDR, have some sensitivity to electrical conductivity. Electrical conductivity is highly correlated to temperature. As temperature goes up, electrical conductivity goes way, way up. And so if you're in a really salty soil, you might see some positive correlation between temperature and the measured water content. And this is due to the electrical conductivity sensitivity, even if it's really small in the sensor. If you're in kind of a middle range of electrical conductivity, then maybe those two effects cancel themselves out. And we've certainly seen this a number of times, that in some soils that have low to medium electrical conductivities, there's really no sensitivity to temperature at all. The bottom line here is that the temperature sensitivity that you see in your data set is probably dependent on the soil type. So this is something that we can't correct on the sensor itself. This is something that you would need to correct out in post-processing when you're doing your data analysis, if it's large enough to actually be a problem, which it typically isn't. Typically you're talking about sensitivities on the order of maybe plus or minus 1% water content, which a lot of people find acceptable. Okay, so let's look at what these errors in measured dielectric permittivity translate into in terms of water content. So the accuracy spec that we set for a lot of our digital sensors, for our calibrated sensors, are plus or minus 1 unitless dielectric unit from dielectric permittivity of 1 to 40. And that range of 1 to 40 ranges all the way from air up to about saturation in a typical mineral soil. So if you vary the measured dielectric permittivity in that mixing model that I showed you and look at how that changes the water content, then you'll see that, that at low water content, that's about a plus or minus 3% or 0.03 cubic meter per cubic meter change as you change that by plus or minus 1 dielectric unit. And as you go higher in water content, that error gets quite a bit lower. So this is about worst case. This is what you can expect when you have a whole bunch of sensors, and those sensors are varying amongst the population, that some sensors might read as much as plus or minus 3% water content different from each other. And this is one reason, this is one of the small reasons why you might measure a negative water content. If you look in the lower left portion of the graph here, maybe a sensor that's measuring permittivity perfectly here measures 0 at 0 water content, but if you get a sensor that's a little bit of an outlier, that may measure as much as negative 3% water content. Okay, so that's one reason why you might get a negative water content out of your sensor. So let's switch gears and get away from the sensor accuracy, and let's talk about the relationship between dielectric permittivity and volumetric water content. So once you get that permittivity measurement, you're only halfway there. You need to, of course, convert that to water content, and you would use what we commonly call a calibration equation. Unfortunately, each soil really has a different relationship. Okay, so the relationship between permittivity and water content is a little bit different for each soil. Fortunately for us, most mineral soils, most typical mineral soils have a pretty similar relationship. But once you start getting out of the typical soil range and get into high bulk density or low bulk density or real high organic matter or specialized mineralogy, then that generic relationship doesn't really hold anymore. So these relationships that we use to predict water content from dielectric permittivity are generally determined empirically. And as I showed you before, that top equation has been used many, many thousands of times as a generic way to get from dielectric permittivity to water content. Now, one thing I have to stress here is that the sensor manufacturer cannot control or specify this relationship. This relationship is determined strictly by the soil or material that you're putting the sensor into. So this is not something that we can take into account in hardware or take into account in software. This is something that is an intrinsic property of the soil itself. So let's look again at that mixing model, and let's tweak some of the parameters that go into that mixing model over ranges that correspond to normal soils and see what that does to our measured water content. So I think we all know that the bulk density of the soil varies quite a bit from place to place and over time, in fact. So in agricultural soils, we typically look for bulk densities on the range of 0.8 to maybe 1.8 grams per cubic centimeter. If you vary that bulk density parameter in the mixing model from 0.8 to 1.8, that gives you about a plus or minus 2% error in measured volumetric water content. And that's just over typical ag soils. If you start looking at peat-based soils, volcanic soils, highly compacted soils, maybe in a road bed, those errors can be much larger than plus or minus 2% volumetric water content. So this starts to get you to think a little bit about the assertion that any sensor could measure volumetric water content within 1 or 2% in any soil. Well, already we're looking at 2% volumetric water content changes just from changes in bulk density over a relatively narrow range. So let's move on a little bit and look at what happens when you're measuring in soils that have different mineral permittivities, different mineralogy, different minerals have different dielectric permittivities. The dielectric permittivity of soil minerals is typically between 3 and 7. This already represents a plus or minus 2.5% error in the water content measurement. Okay, so that already blows the claim of 1 to 2% water content accuracy in any soil, blows it right out of the water. Okay, and this gets a lot worse if you start looking at real specialized soils or soils with really odd mineralogy. For instance, titanium dioxide minerals have a dielectric permittivity of over 100, and you're talking about tremendous error if you're measuring in something like that. So you wouldn't really have to worry about that in most soils, but that range of 3 to 7 already gives you plus or minus 2.5% water content error. What about the effect of dielectric permittivity on of water? Okay, so dielectric permittivity of water is about 80 at room temperature. As you increase from that, you have about a decrease of about 0.5% per degree C. And so, of course, in dry soil, there's no error from this at all because you don't have any water there. But as you go higher up in water content, you can see that for a range of temperatures from 5 degrees C to 45 degrees C, which may or may not be a typical range that you'd see over the course of a year in your soil, but it may be, then you're talking about plus or minus 3% water content error just from the temperature sensitivity of the dielectric permittivity of water. Okay, so you're starting to get a sense now of how much error these different factors can introduce into the measurement. We were talking about the temperature sensitivity of the dielectric permittivity of water. There are also other factors that affect the dielectric permittivity of water. When water is in the soil, it doesn't behave exactly like it does when it's in a say a glass or a pool, where the water molecules can polarize freely. Some of that water in the soil is closely associated with soil particles and is bound to those soil particles or organic matter. And this causes that water to not be able to wiggle or orient itself as quickly and makes it invisible to a high frequency measurement. So in some clay soils or very highly organic soils, the high frequency measurement techniques, TDR and TDT, can be significantly affected by the bound water, meaning that bound water won't show up, that you won't see that water with those measurements, and the dielectric permittivity and corresponding soil moisture measurement will be too low. Typically, the capacitance or frequency domain instruments that operate at a lower frequency aren't affected as much by that bound water. Of course, the lower frequency sensors may have more electrical conductivity, sensitivity, so there's kind of a trade-off there, but it's something that you need to be aware of. So over the last few slides, I've kind of painted a little bit of a gloom and doom picture, saying, okay, from bulk density, you're looking at losing 2% volumetric water content accuracy. From just the temperature sensitivity of water, you're looking at losing 3% from these various factors, and you're starting to get these big error bars, but those are really kind of worst case. So let's look at what we actually see in practice when we look at the relationship between dielectric permittivity and water content. So this graph shows, this is actually the calibration data set that we used way back, it's got to be almost a decade ago now, with the EC5 sensor. You can see on the x-axis is sensor output, and in this case it's millivolts, but you could think of that as being dielectric permittivity. On the y-axis, you see the true volumetric water content that was obtained by loss on drying, like we described. And you can see that for a whole range of soil textures, this topsoil this is a sand, this is a Patterson sandy loam, this is a Palouse silt loam, this is a Houston black clay, which is a really nasty vertisol. And then you can see that each of these was prepared at several different electrical conductivities. And if you make sensor measurements over a range of water content in those, you can see that you end up with actually a pretty tight relationship. And so what we do is draw a best fit line through this. That's our blue line, and that's our calibration equation. And then if you take the 95% confidence interval on both sides of that, you'll see that that corresponds to about plus or minus 3% volumetric water content. So we don't particularly like doing this, but our customers demand that we give them a relationship between sensor output or dielectric permittivity and water content a generic equation that they can use for at least a first approximation. And this is the relationship we give them, and they also demand that we give an accuracy spec. Okay, how accurately can we measure water content with these sensors? And you can see here that 95% of the time you are within plus or minus 3% volumetric water content in a range of typical soils. Now these soils span a whole range of textures and electrical conductivities, but all are still typical mineral soils. And so that's why we say something like these sensors can measure within about 3% volumetric water content over typical mineral soils. Okay, and we think that's a pretty honest spec and a pretty good way to state it, even though we really can't control the soils, but this is about what you'd expect in real practice. But if you take a closer look at this graph, you will see that the use of this generic relationship, this generic calibration relationship, can also cause you to read a negative volumetric water content with your soil moisture sensor. So if you look over here, you'll see that this relationship, or that our generic calibration, if you extend that all the way down to the sensor output, in this case 400 millivolts, that you'd see in this sandy soil in a very dry soil, well, that relationship predicts negative 2% water content. So if you're seeing in a very dry soil a negative 1 or 2% water content, then this may be something that's just related to the relationship that you're using to get from dielectric permittivity to volumetric water content. So let's talk about when a generic calibration like the one that I just presented fail, when you might not want to use that generic relationship that's given to you by your sensor manufacturer, or that generic top equation that's so commonly used. If you have soils that are not typical soils, if you have organic soils, peat soils, real high organic matter content, then those are not going to be well approximated by one of those generic calibrations. Volcanic soils, soils with odd mineralogy, for instance titanium soils, those you're gonna get a really bad water content accuracy if you just use a generic calibration. Soils with abnormally high electrical conductivity. Okay? In the case of our sensors, if you get above a saturation extract electrical conductivity of about 8 decisiemens per meter, then that starts to drive the sensors a little bit nuts, and you would have to do a soil-specific calibration. You wouldn't be able to use the generic calibration. Now this is especially important. You would certainly not want to use a generic mineral soil calibration in non-soil growing media. So for instance, if you're working in a greenhouse or a nursery in potting soil or peat or rock wool or perlite or cocos or any of these things that people grow plants in, those are not going to be well approximated with the generic mineral calibration. And so you would need to either ask for a specialized potting soil calibration or do your own soil-specific calibration. Also, even if you are working in a typical mineral soil, but you need volumetric water content accuracy better than about 0.03 meters cubed per meter cubed, or better than 3% volumetric water content, then you'd better do a soil-specific calibration to make sure that you're getting the kind of accuracy that you need. So let's now talk about, I've alluded to it a couple of times, I get ahead of myself, sorry, but let's talk about soil-specific calibrations. What do I mean when I'm talking about a soil-specific calibration? What I'm talking about is determining the relationship between dielectric permittivity and water content for your particular soil. And this is really a key for getting the best accuracy out of your dielectric sensors. So there are several methods, really two main methods that people have tried. One of those methods produces really good results, and one of those methods doesn't produce good results at all. So hopefully I can save you a little bit of time and energy by talking about this for a few minutes. When you think about determining the relationship between your sensor output and water content, almost invariably the first thing that pops into your mind, I know it was the first thing that popped into my mind, was to use a dry down technique. So with this technique, you would start with a wet soil in some container. You'd put a sensor in that soil and measure the sensor output as that soil dries down. If you're also measuring the mass change of that sample, then you're measuring the water content of that sample. So if you're measuring water content kind of continuously and you're measuring the sensor output continuously, then you can come up with a calibration equation that relates those two together. There are several big problems with this, okay? Some benefits, okay, but I think that the problems and the limitations outweigh the benefits. The benefits that you see here are twofold. First, it really kind of appears to mimic environmental conditions. Generally, in nature, you are measuring water content. You see pulsed events where the water content shoots up, either irrigation or precipitation or snowmelt or whatever it is, and then a slow dry down as the soil drains and the water evaporates away. So this kind of mimics those conditions. Probably the bigger benefit is that you're working with an undisturbed sample. So the soil sample maintains its structure, which can be a little bit important, but there are some serious limitations. The biggest is that the results from this method are highly dependent upon where the sensor is inside the container. So if you look at the graph I have down here, you can maybe see a little bit better about what I'm talking about. So the blue line, this is the top equation. This is just a calibration equation that's been determined using the method I'll talk about in just a minute. But this red line is the calibration equation on that same soil used with the dry down technique. So what happens here is you start with this very wet soil, okay, and everything's homogeneous. And so you get a good point. But then the soil starts to dry down, and so you see a big, steep decrease in the volumetric water content, okay? But you don't see a corresponding decrease in the dielectric permittivity. Why is that? Well, if you spend much time working with soils, you know that when soils dry out, they don't dry out evenly from the entire profile. You end up with pretty much a discrete drying front, so that soil, if it's only open to the atmosphere on top, dries down from the top, and there's wet soil all down here with a dry layer that starts to penetrate the soil and go deeper in the soil. Well, you're getting loss of water, so you've lost volumetric water content, but that loss of water isn't occurring where your sensor is measuring. So the sensor isn't measuring really any loss of water at all. And so you end up with this S-curve where it starts off with the sensor not picking up any of that water loss, but once that drying front reaches the space where the sensor is measuring, then you get this relationship where you lose a lot of dielectric permittivity for a little bit of water content loss, and then once that drying front moves past the sensor, then you end up with again this steep change in water content over a little bit of change in dielectric permittivity. And this is invariably the type of curve that you get with that method. And this is going to give you some pretty horrid accuracy when you try and make those measurements in the soil, when you try and apply this calibration equation to the measurements that you're making in the soil. Now, there are some variations on this that have been tried, and you'll see over here in the picture that this is a soil sample with some sensors in it and some plants growing in it. And some of our friends in Spain came up with this idea that if you put some plants on there and let them root into the soil, then those pull the moisture really evenly from the soil, and so you won't end up with this discrete drying front. And they tried it, and we tried it, and it didn't really work. So it seemed like a really good idea at the time, but as it turns out, it doesn't work much better than what you see. You still have a lot of heterogeneity in the soil moisture with that method, and it really makes for some poor calibrations. And it also takes a long time to grow your plants and get that going. So the method that we do recommend, and the method that we commonly do, and that ourselves and many others have had good success with, is the homogenized soil calibration method. And this is what we recommend. So let's walk through this really quickly. What you would do is first start with an air dry soil, air dry it, sieve it out to whatever size fraction you want, and then pack that soil to a desired bulk density. Remember, we looked at the sensitivity analysis and saw that the bulk density of the soil does affect the water content accuracy, so you want to have some idea of what the bulk density of your soil is in the field, and you want to replicate that when you come into the lab and do this calibration. So, pack that dry soil to the desired bulk density, insert the sensor, get several sensor measurements, get several measurements of dielectric permittivity in that soil. Okay? And then here's the key part. Now you need to actually know what the water content of that soil was. So the method that we commonly use is to collect some subsamples of known volume. So you would use a sampler of some type that you know the volume of that sampler, so you can collect a known volume of that soil, weigh it, dry it, weigh it to get the volume of water lost, and that gives you your direct measurement of volumetric water content. Okay, so that procedure right there gives you 1 point. Here you have dielectric permittivity and volumetric water content at 1 point. Okay, so now you add some arbitrary amount of water to that soil and homogenize it again, mix it up again. So we often add enough water to increase the water content by about 10%, or 0.1 meter cube per meter cubed. So once you've homogenized this water in, then you have a little bit more moist soil. Then you repeat the process. You pack it back to the same bulk density, you insert the sensor, take your sensor measurements, you collect some subsamples and get the true water content, and that gives you the second point. Then you add some more water, do it again, add some more water, do it again, add some more water, do it again, and maybe you end up with 4, 5, 6, 8, who knows, as much resolution as you want, but you end up with this data set that shows the relationship between dielectric permittivity and volumetric water content for your soil. You fit that with some mathematical model or some equation that you can use then to convert from your dielectric permittivity measurements in the field to volumetric water content. If you do this, well, let's talk first a little bit about the benefits and limitations. The benefits here are pretty big. First of all, the fact that you homogenize the soil prevents those problems with the drying front and prevents the problems with water loss from areas that the sensor isn't actually measuring. Second, those volumetric subsamples give the true volumetric water content by oven drying. So you're correlating this back to our primary and our direct measurement of water content. And really you don't need a lot of specialized equipment for this. You need some kind of volumetric sampler, but those are pretty easy to find online, or you can just make one. We used to make these out of sharpened conduit pipe. You just need something that you can take a soil core of known volume. Probably the biggest limitation of this method is that you have to use a disturbed soil sample. You cannot maintain the structure of your soil. The errors that you get from disturbing the structure of your soil when making a dielectric measurement of water content are relatively minor. In fact, they're very small, especially when you compare them to the errors that you would get from using that dry down technique. So it's a little bit of a drawback, but it's nowhere nearly as bad as what you might see if you use that dry down technique. Also, another limitation is that in some materials, maybe for instance coconut husks, or maybe a really stringy peat material, or maybe a really stony soil, it's really impossible to collect those known volume subsamples of the soil. If that's the case, then it is possible to do this by weighing the mass, by taking the mass of the entire container if you precisely know the volume that you filled your soil to. So because you're packing that to the same bulk density each time, if you pack it to the same volume each time and you measure the mass, then from that you can work out the volumetric water content from the whole sample. And we actually do that quite a bit on non-soil materials. So this homogenized method is something that we highly recommend to our customers. we've spent some time writing down what we think is the best method to do this. And so we have some step-by-step instructions on our website if you want to go look those up. We also feel strongly enough about this that we offer a calibration service where our customers can send in a sample of their soil and we will do a soil-specific calibration for them. And at this point, we've done hundreds of those for our customers in soils and in non-soil media. My preference would be that you do this instead of us do it. I mean, we're happy to do it, but I think that the benefits, there are other benefits that you would get from doing this yourself. It really helps you be familiar with some of the pitfalls on the probe and probe insertion and gets you some good hands-on experience with the probes before you take them to the field. So either way, if you need really accurate measurements or if you're working in a non-typical soil, then the soil-specific calibration is a good idea. It's always a good idea, but sometimes you don't need it, but sometimes you do. We think, and we've demonstrated that with some care, if you're good at this, then you should be able to get volumetric water content accuracy to within 1 or 2% water content in just about anything. Okay, we've done this for chicken litter, we've done this for wheat bran, we've done this for all the non-soil growing materials, and we think that you can get pretty darn good accuracy if you use this method. Okay, so we're getting close to being done. We've talked about two things that affect your accuracy. The first is the sensor's ability to measure dielectric permittivity accurately. The second is converting from that dielectric permittivity to volumetric water content correctly. Okay, now let's talk about the third, which is the installation quality and some techniques for improving that. This is something that is often overlooked, but something I want to really stress here. In my opinion, the single largest source of error in measured water content is poor installation. Even if you have a sensor that measures dielectric permittivity perfectly, and you have the perfect calibration equation to get from permittivity to water content, if you don't take care and make sure you get the sensors installed properly, then you're going to have bigger errors from that poor installation than all of your other errors combined. So this is something that's really important, and so I want to spend a little bit of time talking about it. Okay, why is this? Why is it that having the sensor installed a little bit poorly or having some gaps around the sensor might give you big errors? Well, if you look at this, this schematic I have here, you could think of these as being the two prongs of an EC5 probe, either facing straight away from you or straight towards you. So you're looking down the probe. These red lines show the electromagnetic field that is generated by that sensor when it's measuring the dielectric permittivity. And what do you see? You see that right near the sensor surfaces, those field lines are extremely concentrated. And what that means in practice is that the sensor is most sensitive very close to its surfaces. Okay? It has sensitivity out away from the surfaces, but it's going to be most sensitive very close to its surfaces. Well, what happens if you put a sensor in and you wiggle it to the side? Where might you get a gap? Okay, where you don't have good contact with the soil. Well, that gap's always going to occur closest to the sensor. Okay, right where you have the most sensitivity. So if that happens, then instead of measuring soil and water, you're just measuring air, and so this gives you big errors in your measured permittivity and therefore your measured your measured water content. So here we have it that those voids or air gaps typically occur near where the sensor sensitivity is greatest. And so this can give you a massive underestimation of the water content. And this is by far the biggest reason that your soil moisture sensor might read negative. Okay? We looked at the errors from sensor accuracy, we looked at the errors from converting permittivity to water content, and those are generally on the range of 2% or 3%, maybe a little bit more if they compound on each other. The errors from poor quality installation can be 10%, 15%, 20%. They're far bigger than all of those other errors. And they're almost always in the negative, they almost always push the output of the sensor down. So it's really easy to get a negative volumetric water content measurement just from air gaps around the sensor. Let me take maybe a couple of minutes to tell a story. Back when, well, not when I first got to Decagon, but after we finished up the Mars probe project, I spent a lot of time working with customers, doing customer support, and I was on the phone or on email with customers every day. And so I heard a lot of people say, "Hey Doug, you know what's going on? I've got measurements that are negative. There's no such thing as a negative water content measurement." And I'd say, "Yeah, you're right. How negative are they?" And if they said, "Well, you know, my soil's pretty dry and it's measuring down about negative 1% water content," then that's when I would think, well, that's probably not a big deal. That's probably just because you're using a generic calibration equation and it's given you some small error at the low end. So don't worry about it. When your soil wets back up, you may have a, you know, plus or minus 1 or 2% error there. Not such a big deal. But if they said, well, it's measuring, you know, 8%, negative 8% water content, then that's when I said, oh, you got a problem. You've got an air gap around your sensor for some reason. And it's not always because the person who installed it did a bad job. I'm not trying to blame people for that. Sometimes it's because it wiggled when it went in, but other times other things happen. If a crack forms around your sensor, then you're going to get negative readings almost immediately. We've had instances where worms have come and burrowed right up against the edge of the sensor and left a big biopore there, a big air-filled void, which will give a negative measurement. And so we've certainly had a lot of instances where you dig down and you look at the sensor and you can see pretty much immediately what's going on. It's actually interesting what you see when you get in the soil and look at what's going on around your sensors. So let's talk about a little bit more. I'm talking specifically about air gaps previous to this, but you also can get some errors that are due to installation if you don't install the sensor into undisturbed soil. It's always best to insert that sensor into undisturbed soil because then you're measuring the native bulk density. If you pull out a bunch of soil and disturb it and put your sensor in the bottom of a hole and try and pack that soil back down over the sensor, then you may not have achieved anywhere close to the same bulk density of the surrounding soil. And as we saw in our earlier analysis, that can give you some pretty substantial errors in your water content measurement. So there are really two main methods that you can use to install the sensors into undisturbed soil. With the first of those, you would do what's called a sidewall installation. And with this technique, you would dig a pit or a trench in the soil, okay, smooth off a face so you have a nice smooth face of undisturbed soil, and insert that sensor carefully into the undisturbed soil in the sidewall. Then you would backfill the trench, of course, and try and maintain the native bulk density. And this is a pretty good method. This is, if you have the time and the resources to do it, it's actually a pretty good method. The real advantage is that while you're inserting that sensor, you have visual and tactile confirmation that you've inserted that sensor well. You can feel and see if that sensor wiggled and gave you a big gap, or if you hit a rock and displaced the sensor. And if something like that happened, you'd pull it out and go to a different spot and try and insert it and get a good quality installation like we've talked about. The other advantage of this is that you have undisturbed soil above the sensor. So right above the sensor, there's undisturbed soil, so you're pretty confident that your flow characteristics in that soil are undisturbed and representative of the rest of the soil profile. Also, you can get a horizontal insertion, which gives you a discrete measurement at a certain depth in the soil. And this is probably still the most common and most accepted method that you'll see in the literature. So many people still do this. Go out with a shovel or a backhoe, dig a trench, shave off the sidewall, and install your sensors. There are a couple of disadvantages. First of all, this takes a lot of effort. Okay, you have to get out there, you have to get this hole dug. and also you have a large-scale soil disturbance that's in pretty close proximity to your sensor. Granted, you have undisturbed soil immediately above the sensor, but adjacent to that, you have some plane through the soil where you dug that trench that's a possibility, that gives you the possibility of preferential flow and things like that. So there are some drawbacks. The alternate installation technique is a downhole installation technique, and with this technique you'd use an auger of some size and auger a hole to the desired depth and then insert the sensor into the undisturbed soil in the bottom of that auger hole. You can see on the right side, this is a vertical installation, and that installation is the easiest in terms of effort because your hole doesn't have to be as long, but it does open the possibility of preferential flow above the sensor coming down to the sensor, and also you certainly have disturbed the soil immediately above the sensor, which can give you some changes in the flow patterns above that sensor. So what I recommend if you need to do a bunch of different a bunch of sensor installations and you don't want to dig big pits is to use an auger hole at about a 45-degree angle. And you can see that this is kind of the best of both worlds, that if you've got the 45-degree angle, you still have minimal soil disturbance, but now you have undisturbed soil above the sensor, and so your flow characteristics above the sensor are undisturbed. Downhole installations have some advantages. First, you can go really deep with these. You can auger a hole about as deeply as you want, and as we talked about, you have pretty minimal soil disturbance. It's just a little auger hole. There are some disadvantages though. First, it's not really possible to verify that you have a quality installation. So with the sidewall technique, you pretty well know when you insert that if you have a good installation, but if you're working with a sensor that's 2 feet down on the end of some installation pole, then you might have a good idea that you got a good insertion, but you don't know 100% for sure. Also, you need to dig an individual auger hole for each sensor. So if you're doing soil profile work, then you need, for instance, if you want to measure at 5 depths, you need 5 auger holes at each spot because you want to insert that sensor into the undisturbed soil in the bottom of each auger hole. And finally, you do need some type of installation tool. And in the picture, you'll see a PVC, a piece of notched PVC that makes an adequate installation tool. There are much better ways of doing this with, with steel installation tools that hold the sensor straight a little bit better than the PVC would, but you can get pretty creative with that. So we often get the question, hey, all these things that you're telling us are great if you're working in the Palouse where I am, where there's no stones in the soil, but what if we're working in soil that's got 45% rock in it and stones? How do we install the sensors in that? And this is extremely difficult. If you're just working in hard soils, maybe a clay soil that's a little bit dry, then you can use a pilot tool. Okay, you can develop a pilot tool that's just a little bit smaller than the sensor, but shaped similarly to the sensor, that you can pound into the soil, make a pilot hole, pull that out, and then install the sensor. So this works pretty well, but in stony soils, even that doesn't work because you hit a rock and it moves it to the side. You've got a big air void and you're getting into the air gap problems that we've talked about. So really, in stony soils, your only solution that you're left with is trying to remove some stones from the soil where you're going to install the sensor. So if doing that, you would pull out a bunch of soil, sieve out the stones, and then in this case you would have to pack the sensor back into some disturbed soil. It's not great, but if you do a good job of replicating the bulk density of the surrounding soil, then you can get decent measurements. It's certainly not a perfect solution, but it's as good as you have. Stony soils are just very difficult to work with, and there's not really a great solution to that. Okay, so I know I said I was only going to talk about 3 sources of error, but I do want to touch very briefly on a potential 4th source of error, and that is scaling from a point measurement with a soil moisture sensor to the field scale. So all of your dielectric sensors, I don't care what they are, have a really small, relatively small measurement volume, from tens of cubic centimeters to hundreds of cubic centimeters. So you're talking about a small soil volume, and trying to scale a soil moisture measurement from this scale up to the field scale is very difficult. So there are several strategies for that. A lot of people will simply make a lot of measurements and average those and try and come up with a good field scale. But there are other strategies available, and the geostatisticians work on this all the time. There's whole branches of science that are working on this, especially now that a lot of people are trying to use soil moisture sensors to validate satellite-based soil moisture measurement, but that's really outside the scope of this discussion. So I just wanted to point out that that issue is there, so you should pay attention to that when you're using these point measurements. Okay, so that's what we had for today. I'd like to make sure that I reiterate a few take-home points, things that I'd like for you to remember when you walk away from this presentation. First of those is that there are really three main sources of error in your volumetric water content measurement. The first is the sensor error, which is basically the accuracy with which the sensor can measure dielectric permittivity. And this is the only thing that I can control from here at Decagon, or others can control from their manufacturing facilities. The second source of error is the conversion from dielectric permittivity to volumetric water content. And this depends on a lot of factors in the soil: bulk density, temperature, mineralogy. A generic calibration will generally work for most typical mineral soils, but if you're working in non-typical soils, then you need to do a soil-specific calibration. It's really important if you need good accuracy. That is the third take-home point, is that the sensors need to be installed correctly. So if you look at the errors that you might get from those different factors, okay, here's the sensor accuracy, maybe plus or minus 3% water content, bulk density plus or minus 2, mineral permittivity 0.25, 2.5% permittivity of water, 3%. Just note that all of those are really small compared to the error that you get from poor installation, which can be 10% or even greater than that. Okay, thanks a lot.